Okay. And what I can do is I can just run index rate like this dot star slash star stream, and so then it will run over all of them, and so you can see it's almost done, and we can clearly see that basically anything between 907, isn't it? And what? 932, is that it? So we can see it between 902, isn't it? Sorry, 907 and 932. It's basically the same. You see, it's 24.2, 24.4. Basically, they're all the same. There is not much we can do there to improve or anything. Okay, so that's why the next thing we want to do is to actually use the shape of the unit cell to actually calculate which one produces the best unit cell. Okay? So how do we do that? Well, in theory, it should do it by itself, but it cannot because it's stupid. Okay, so more. Let me see if distance scan analysis. Was it this one? Yeah. Exactly. So hopefully this one works. Okay, so we can do Python distance scan analysis minus f. Okay, and it would be course. Let's see if it works. Will it? Will it? Will it? No, it did not. So this one doesn't work either. Okay, so if this one doesn't work, well, we can use eval, which is my own script, which is much worse than this one. But hey, it is.
Just turn on the light.
Yeah, it is what it is. So what do? We copy eval to course, okay, and we copy where is it plot. Is there no plot here? Okay, there is no plot here. mmcpd2 178 79 to 180, and then blend test, and then I want to copy, what is it, eval.sh and plot.gp. Okay, and now I want to see eval.sh how it looks like. Okay, so now we copy eval.sh into course, and we copy plot.gp into course. Okay, and then we go into course and module available, and I want to see GNU plot. I want to look how to load GNU plot. Here, GNU plot. Okay. What is it? Module load GNU plot. Okay. Okay. So should load it. Okay. So, and now we do cp star stream. So I'm just copying all the streams out here, you see? And so now if I run eval, we're missing stdev. Okay, let me just remove star.png. Copy course, now all the scripts that are necessary are in there. And so now if we run eval.sh, it should work. Let me see. STDF is here. Remove out. Remove start.png. Ah, I know. Start.png. MCP STDEV to course. And now we go into course where all the data is. Okay. And I remove just in case out. Okay. And I now run eval here. And so what is this going to do? STDEV extracts all of the unit cell information from all of the streams and produces a standard deviation, so it calculates the standard deviation from it. So, and it produces this file here, out-geom-ref.txt. So if we open that file, now we see the detector distance here. Yeah? So that's the detector distance. This here is the number of indexed images, the total number of images, the A-axis in nanometers, the standard deviation of the A-axis in nanometers, the B-axis in nanometers, the standard deviation of the B-axis in nanometers, the C-axis in nanometers, the standard deviation of the C-axis in nanometers. Now what we want from here is actually the standard deviation. Why? Because crystallization is a stochastic process. And any stochastic process will tend to produce a population that is normal. Okay? So, and a population that is normal, the narrower that population, isn't it? The lower the standard deviation. But also the more, given a certain number of members in a population, the shape of the distribution that will produce the smallest standard deviation will be the normal distribution. If you want me, I can show it to you. I don't think we need this one. So, and I have, yeah. Basically, what I'm saying is, this is a standard population, isn't it? It's symmetrical, and the standard deviation is here, isn't it? That would be the standard deviation. Now, imagine that we have the same center, but it is highly asymmetrical. Now the standard deviation is this. You see? In the opposite direction, it would be the same. So, for the same population, the same number of members in the population, the normal distribution will have the smallest standard deviation. Therefore, So therefore, what this means is that by looking for the smallest standard deviation, we're gonna find the most normal distribution, and we know that because of the way crystallization happens, the best descriptor of the process of crystallization will be the most normal distribution. Thus, the detector distance that gives us the most normal distribution will be the best detector distance. Okay? Notice that this is only true if we have probed the same number of crystals. So you will see it in a moment that, so when we open the files, okay, so let's see. Exactly, so now we have here, so this also produces these files that are the ones that are nice to take a look at. So we can do composite.png, okay, and hopefully it'll open it. So to open the file, to open an image file, I use EOG, okay, and so you can see it here very nicely, okay. Here we have the what's called the number of indexed images, sorry, not the number of indexed images, the percentage of indexed images. And so we can see how it grows, and then here we have a certain number of detector distances. So this is the detector distance, of course. Here we have a number of detector distances that are all the same, isn't it? I mean, like they all produce the same amount of data, so we cannot discriminate between them by indexing rate alone. And then the hit rate also goes down on this side, isn't it? So clearly, as we collect the data, you can see that here we have a sort of linear but opposite relationship between the standard deviation, between the number of index images, or the index rate, and the standard deviation of each of the unit cells, of each of the unit cell axes. You see, as we increase the hit rate, the standard deviation goes down. Okay, remember the number of the standard deviation is correlated to 1 divided by the square root of the number of measurements. So we expect that for a constant uncertainty, increasing the number of measurements will lower the standard deviation. However, this region here all have the same number of images, isn't it? You see it here, approximately. So they differ from each other by somewhere between 10 images, 20 images, something like that, over 2,500 images. Therefore, these in principle have the exact same, should have the exact same standard deviation, unless there is something else going on. And indeed, when we take this region, we see that there is something else going on. We can see a clear point here, which is by far the one with the lowest standard deviation. So there's A, B, and C. So you can see green, blue, and orange. That corresponds to A, B, and C. But the most interesting one is this pale yellow one. So this one here. You see? This one here. That is a ponderated average of the standard deviation for all of them. So that means if for the longer unit cells, that's C, okay, so where is it? C here, it has a higher standard deviation, so it considers it more important than the other two that have lower. So the detector, what's it called, the value of the A and B axis is smaller, so it has a lower standard deviation by itself because the number is smaller. So this one here, the composite, okay, it's a mix of all three, and it gives you a pretty good value of where it should be, where we have the smallest one. And we can see that it's very clearly at 9.22. Okay, so that means that now we know quite nicely that 9.22 is the best, the best value. So, okay, so now we can go and we can confirm it again by going to 9.22, and notice that. So we can go into this folder, okay, and notice please that if we go here to 9.22, notice that it's not necessarily the one with the highest number of images. Notice that 917 has more, and 927 have more images. However, the standard deviation clearly is lower, so that's the one we want to take. You can see it again, 0.91. Meanwhile, the next one is 0.12. You see, so there is a pretty significant jump in the standard deviation, even though we're getting more data from that one. But the quality of the data is going to be better in this case. So what we can do is do cell explorer for 0.0922.string. Okay. And there you have it. Looks absolutely beautiful. Okay. See? And so we can do what's up? So, do like this. And yeah, you can see very nice unit cell. Okay. So the next thing we can do is actually use this one. So by comparison, we can also take a look at 0.0917. Okay. Actually, we can do it from here directly. Cell Explorer 0.0917. And you can see quite clearly that this one is skewed. This side is a lot more So if we compare, okay, so let's go and do the comparison. So here we have this one, and if we look here, see the difference?
Yes.
Quite clearly. Okay, this one is better than this one, and so there you have it. Okay, that's how we get the data. Okay, now very importantly, also from here we can calculate the unit cell. Okay, and so we do like this, we shift. And now from now on, the most important thing is not so much getting the best unit cell, but getting a unit cell that is very close to this one. Yeah, so now we save this, create unit cell file. And we're gonna call it crackery.opt.cell. Okay, and yeah, save. And now, so now we can close these two. Okay. And what we want to look at this is the unit cell that we had provided initially, okay, and this is the unit cell that we ended up calculating, and you can see it's almost identical, not quite. Okay? Now the difference is not not very important, but we should, from now on, we should use this one probably.
Oh,
okay, so that means that from now on, when you do the other ones, we should use crackery opt.cell as our. So let's go to sample. Where is it? Samples folders, and this stopped, and we copy it in here, okay? And then we copy everything basically, okay, into because we know that these ones work, and so now you have everything that you need in there, except you now need to delete all the LST, because if not, you're going to be running on the same file, isn't it? Okay, good. So I'll do that in a moment. Let me just do remove sample folders, desktop star.lst. Okay, I'm just deleting the list files from desktop so that we don't have them in there. Okay, good. So now we have the data that we need in there, okay? And now we know which unit cell to use. So the next thing that we need to do is go to 0.0922, okay? And once here, we run detector shift 0.0922.geom 0.0922.string. Let's see. The opposite way around. This? Yes. So, and what this is going to do is, at some point it will open it, it will check where so how much of a shift the detector has. What does this mean? Okay, well, we'll take a look at a moment. It should have almost no shift. Yeah, it has almost no shift. It had already a very, very good detector, so we don't need to really shift it from its original position. So what are we looking at here? The little dots you see here, okay, those corresponds to the center of the image, So the H0, K0, L0 for each of the indexed crystals that we have in the data set. Okay? So from there it calculates an average center, which should be the position 0 for the detector. And that we see in blue. Yeah, it's 0, 0. Okay? So, and then it calculates how much it should shift that position in the calculation, okay, to move it to where the actual geometric center of the actual detector is. And that's that position there. And so now each pixel, if I remember correctly, it's 0.001 millimeters. Okay? And as you can see, that is well below that. So that means that we're very much within the region where the theoretical center and the real center are at under 1 pixel difference. And if something is under 1 pixel, you simply cannot detect it. Isn't it? That's the whole point of the resolution of a camera or of a detector in this case is simply, what it means is that if two things are closer together than 1 pixel, then they will appear on the same pixel, and therefore you cannot tell the difference between the two. So if the theoretical center and the real center appear within 1 pixel of each other, that means that we have refined the XY position to the best position, which means that this is now our original geometry. Okay, so you can see this one here. From now on, 0.0922 minus spread refined dot geom. That is our geometry that we will use for full indexing. So what do we do now? We copy 0.0922 minus spread refine to where is it? Full index. Okay, and so now, okay, we should have it in there, and we can also copy it to opt param. Okay, that's something that you can also actually start to do already while the rest is running. Okay, so what do you do now? Well, for the foreseeable future, what you do is simple. You take and do exactly the same that we have done right now, but for each individual injector, so that we know the best detector distance for each individual injector. Okay? Now, very important, okay? If you look at the files, so if you look at here, this of course is only for dark. When you work with the other ones, with one, so well, let's check it. Alvra data P21006 raw run 0018 crackery dark, and we go for data. Yeah, of course, that's only for, so yes, so see, if we take, for example, let's take this one, okay? Run 037 crackery, okay? So now you see when you go to data, okay, so now you will have a dark and a light list. So don't worry, because when you combine everything, you will get an all dot list that combines all dark and light. But for full indexing, I highly recommend that you divide it, because this is the only place where you have a list that is light and dark. You see what I mean?
Yeah.
Okay. For detector distance, it doesn't matter. But when you do the full indexing, you want to take only the dark images and only the light images in two separate folders, so that you get the streams, so the light streams and the dark streams separate from each other. Okay, so yeah, so first thing is to do detector distance. So please go ahead and run detector distance for every single injector. This should take you about the rest of the week. I mean, it should take you about all of next week.
Yeah.
Okay, so go ahead. Okay. Then from there we will do parameter optimization. Once you have the proper distances, we can do parameter optimization, and from there, the next thing is to then do full indexing, and then you will be ready for all the data and produce all the maps and everything. So my guess is end of October you will be solving your first structures.
Okay.